Hello, today we're focusing on floating point number representation.
So floating point representation is what a lot of people think is the most difficult concept in this entire course. It is certainly the most mathematically intense concept. So some students who don't have a maths methods background might find this a little bit challenging. But it's okay, it's only a relatively small part of the course, you can certainly get by without it, but it's still fairly important for everyone to at least see the concepts and the difficulties that we've got. To start with my explanation, let's look at the four types of number that we've looked at so far. In Java, we know that we could store things as a byte, or a short, or an int, or a long, and nearly everything that we've done so far has been dealing with ints. Certainly int is the standard integer type in Java that we use a lot. We'll talk about why that is a bit later on. And ints use 2's complement to store their numbers. They actually use 32-bit 2's complement, and we'll talk about that a little bit later. It's not really relevant for what we need to do now. But all of these four are integer types. They all store numbers using 2's complement. We've also got two other types, number types, that we call double and float. And we're going to look at those right now in detail. Just for completeness, let's also remember that there are two more types that aren't used to store numbers. We've got char, which we've already looked at, and boolean, which we're not going to look at in a lot of detail because it's really just a 1-bit value that is true or false. Let's have a talk now about how these two store their information. So this topic is called floating point representation because both of them use floating point. Floats use 32-bit and doubles use 64 bits. Those are both too complicated for us to look at in a great amount of detail. So when we're describing the concept of the system, we're going to shrink it down quite a bit. And we're going to talk about examples that might be 16-bit or even smaller. All right, we know that integers store numbers like 7 or 3 or 0 or -2 or 138,246. And we also know that doubles store numbers like 2.34 and 7.6 or 3.1415926 or -3, but we'd store it like 3.0. So how do these sorts of numbers get stored? We've already talked about how some of them can be stored exactly and other ones of them can't be stored exactly using binary representation, and how some might have ongoing infinite recursion. But that's not really a complexity for what we're going to do now. Before I go any further, let's talk a little bit about the standard scientific notation. Using our old decimal system, we should know enough to know what 3.26 times 10 to the 7 is. How does that compare to something like 4.36 times 10 to the 5? Which number is bigger? Well, we know that this thing here is 3.26 with 7 zeros after it. So in that case, 5, because we've moved our decimal place 7 spots. So it's gone from there to there. I'm just going to undo so there's no mark there. All right, now compare that to 436, which means we've moved the decimal place only 5 places. So we get that number, 436,000. So it's obvious when we write it out like that this top number is bigger, because essentially this value here, which we call the exponent, this 7 is bigger than the 5. So the exponent essentially tells us the magnitude of the number, how big the number is. And we know that we might have a negative exponent. We might have something like 2.37 times 10 to the negative 4, is this number a positive or a negative number? Well, it's actually positive because it's the number out here that tells us that we're positive, and this negative doesn't mean the number is negative, but rather just means it is incredibly small. So in this case, 0.00237. All right. So either this number down here or this number up here can be positive or negative, and they have different requirements, different notations in they mean different things in scientific notation. Generally speaking, our scientific notation should be written like this: at plus or minus a times 10 to the power of k, where a needs to be a number that is greater than or equal to 1, but is less than 10, and where k must be an integer. If k is not an integer, that's my symbol for integers, which you'll know about if you've studied any maths. If k is not an integer, then it's not scientific notation. And this number here, this a value, must be between 1 and 10. It's allowed to be 1, so we could have 1.00 times 10 to the power of 7. That's a perfectly valid scientific notation number, but 10.34 times 10 to the 6 is not, or sorry, not even if it's 10.34, let's just say 10.00, so that it's actually equal, times 10 to the 6. These two numbers are exactly the same value, but only one of them, this top one, is correct scientific notation. When we're learning about floating point in binary, we're going to be dealing with a very similar representation to scientific notation, except obviously since it's binary, we're not going to be using the base of 10, because this 10 tells us our magnitude and tells us what column it's in. But in binary, which is base 2, all our columns are base 2. So we're instead going to be writing it down. So for binary, our scientific notation is going to be a, our value in front, times not 10 to the power of something, but 2 to the power of k, where a needs to be a value that is between, and this changes a little bit from our decimal system, but here we're going to be defining, let me rewrite that. Here we're going to be defining a as between a half, 0.5, so a must be bigger than 0.5 but is less than 1. Now that means in our binary system, we know that we've got our units column, our twos column, and our fours column. So 110 is 6 point, and if we have 110, then that's our halves and our quarters and our eighths. So this number here is 6 plus a half plus a quarter, which is 6.75. And so what this is telling us, if our a value is between it must be bigger than 0.5, that means it essentially must start with a 1. And we're going to find out that if we're doing this properly, according to this course, all of our a values must be 1. Now I've been calling it the a value before, but it actually has a proper name that you should note. And so this thing here is called the mantissa. That's a word that applies specifically for computer science, specifically for this particular thing. If you look up the mathematical definition of a mantissa, you actually find that it's something a little bit different. So don't do that, I would suggest. Just trust me that for this course, we will just call that thing the mantissa. And as I've said before, we've also got this thing up here that we call the exponent. So our a value is called the mantissa, and the k value is called the exponent. So when we're writing out our binary number, remember, let's talk about a 16-bit floating point. And we actually, every time we define 16-bit floating point number, we need to define how many bits are allocated to the sign bit, how many bits are allocated to the mantissa and to the exponent. And so in any test situation, it will tell you what it is. I'm not suggesting that it changes dynamically. Once we establish what the system is for bit allocation, it's going to stay that way for the entirety of a question. So just to give you an example, let's talk about a system that has 1 bit allocated to the sign, 5 bits allocated to the exponent, and 10 bits allocated to the mantissa. So we can see that there's 16 bits total, and we can clearly see what's going to happen. So clearly see what happens with our bit allocation. What I mean by that is, let's imagine we've got a, hang on, let me also just note, this one's the sign, this one's the exponent, this one's the mantissa. And so in this case, if we have a number like 0, 0, 1, 0, 1, 0, 1, 1, 1, 0, 1, 0, 0, 0, how many is that? 2 more. All right, so this is a 16-bit number. And if you see a 16-bit number and you're told that it's using this floating point representation, we know straight away, okay, well, if that, let's break that 16 into 1 and 5 and 10 by going 1 and 5 and 10. All right, now that tells us that this first number here is our sign. 0 is positive, just like 2's complement, and so we know that our number is positive. Now this number here is the exponent, and remember that k, our exponent, must always be an integer. We've got that definition up here. K is always an integer. So if k is always an integer, the best way to store that is with 2's complement. And 2's complement, of course, caters for positive and negative numbers. So this number here is 2's complement. That means that this is going to be times 2 to the power of, and I'm just going to convert this number, that's a units column, 2, no 4s, and an 8, so that's 2 to the power of 10. And our a value, this is a times 2 to the power of 10, this number here is our a value, knowing that we're using this sort of notation here. Our mantissa starts with this column. So first value of the mantissa is always a 1. That's that one there, which is our halves column. So a is equal to, in this case, a half plus a quarter plus an eighth. Plus there's no 16ths, but 1 over 32. And you may also remember that one way of working this out as a better fraction is to just put the denominator of the smallest value, which in this case is 32, and then convert 1, 1, 1, 0, 1 in binary. So that's the 29. So we have 29 out of 32 as a fraction. We can very easily do that on a calculator, 29 divided by 32, just to get a decimal approximation, which is about 0.91. We'll call it 0.91. So this number here represents 0.91 times 2 to the power of 10, which I can type into my calculator and get an answer of 928. Now, it just so happens that this number is an integer, and we could have stored this as an int, but if we're storing it as a double, we'll put the 0.0 there to make sure that we know what's going on. Now, thinking about how this applies, we've got our to the power of 10. Another way of doing this, by the way, that should give us exactly the same answer, is to take this mantissa. So what I'm going to do is take this mantissa here and put it down there, and write down 11101, which are the only key bits. Now normally our decimal place, sorry, not our decimal place, our binary point is there, but we could also move that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 places, filling out some other zeros. And if we work out what this number is, we know that that's the 1s, the 2s, the 4s, the 8s, the 16s, 32, 64, 128, 256, 512. So that this number here, 512 plus 256 plus 128 plus 32. If I do all that on my calculator, let me type that in, and I get 928. So really we can think of this to the power of 10 as a shift, but it's mostly easier to just do that on your calculator as you need. In this case, what I suggest is that first method that I did of just identifying that it's 0.91 times 2 to the power of 10 equals 928. You can just type that into your calculator, remembering that you're allowed to have your calculator with you in any test or an exam situation. So that's how you would easily convert a number like this to a decimal value. A couple of things to remember are that you may remember all the way back here let's go all the way back here where I'm talking about this bit here. Remember I talked about how our mantissa might be positive and we might have a negative exponent, or we might have a negative mantissa and a positive exponent, and they all signify different things to our number. Well, remember that our exponent is stored in 2's complement, so this one here is our sign bit for the exponent. So that value there is going to tell us whether we've got a really big value or a really small value, and that sign value there is our sign value for our mantissa. There's a lot of complications with this. There are a lot of questions that you might have, and I could answer them, but I don't want the video to go too long. So I might record some Q&A or some clarifications in another video. And at this stage, I'm not even going to worry about how we might go back the other direction. If I've got a number like 27.3642, how might we store that number in the same 16-bit representation? That's something for another video. Before I end this one, though, let's just talk about the complexities of this system. In this case, 0 and... Sorry. I won't dwell on that. We've got 1 sign bit, we've got 5 for our mantissa, and we've got 10 for our exponent. I should point out that this system, this particular combination of 1, 5, 10, is one example that I picked. Your test or an exam that you might be sitting might give you a completely different system. It might say that we've got a 1, 7, 8 system for 16-bit, or it might even give you a 12-bit system that is 1, 5, 6, or various other things. But it will always define what system we are using. The other thing to remember is that we can't change the sign as we go. So just if we're using a particular defined system for a question, that's the system we're going to use for the entire question. So there's a couple of complications that we need to consider with which system we're using. We could obviously have a 1, 5, 10 system with 1 for the sign bit, 5 for the mantissa bit, 10 for the exponent bit. Let's think about how that might compare to a 1. If we add 8 to the mantissa, if we add 3 to the mantissa, we can subtract 3 from there. We still get a total of 16 bits. Let's think about how these two systems might compare to each other. Well, this 8 bits allocated to the mantissa shows us that we can, and remember this is 2's complement, and we know that 8-bit in 2's complement allows a much bigger mantissa. So this allows for a much bigger mantissa. If we think about that in our a times 2 to the k representation, this number here is going to be bigger, which allows us a much bigger range of numbers. Our maximum is going to be higher, our minimum is going to be lower or more negative. We can have a very big range of numbers, and we can also go to very small numbers as well. Why don't we do that all the time? Well, because this 7 here is the number of bits allocated to A, and that's going to be our accuracy. So remember how we can't represent 0.2 perfectly in binary. It's going to be a recurring fraction, a recurring binary point that goes onwards and onwards and onwards. Well, the more bits that we allocate to it, in this case 10 bits, if we allocate 10 bits to storing that fractional part, we're going to get a lot closer to our actual value of 0.2 than we could without it. We can't store 0.2 perfectly. 0.2 cannot be stored perfectly. But we can get close to it. And we'll do this more in the next video. We'll talk about some other complications, but essentially the takeaway message from here has to be we can get close. So I'll write here, we can, this is important notes, we can get close, and the more bits that we've got in our mantissa, so for example these 10 bits, allow us to get closer. Now you might think, why don't we just give all our bits to the mantissa? why don't we give all our bits to the mantissa then? That would allow us to get extremely close. Well, now we've got competing values, because if we've got all our bits allocated to the mantissa, we're going to not be able to have very big or small numbers. That's okay if we're only trying to store the number 0.2, but we might want that amount of accuracy but with larger numbers, or we might want very small numbers. How much accuracy do we want? It's a balancing act. There's no right answer, but one takeaway message is that a bigger mantissa means more accuracy, and as a consequence, less range. And we know that a bigger exponent, which has to come at a cost of a bigger mantissa if we've got a limited number of bits, a bigger exponent is the opposite. It means that it allows us more range, but with less accuracy.